talked about how last week you can get the three equations of motion, the ones that you know well. V equals u plus at, s equals ut plus half at squared, and v squared equals u squared plus 2as. What was the main difference that in deriving those three equations last week compared to how you... All right. We're using calculus rather than just speed-time graphs because it's more flexible. If you can differentiate and integrate, then you can use almost any kind of motion. So really what we're after this morning is varying acceleration motion. Now, you would have thought after doing equations of motion that's higher in standard grade, that would be most of the motion that you need. Things just dropping in free fall, they have constant acceleration. Things which are being driven with a constant force, they have constant acceleration. So from your discussions, what are some of the examples of motion that do have varying acceleration? Things that are either falling and reach a terminal velocity, that's got variable acceleration because the forces that are on it are not constant, so they become unbalanced as the air resistance reaches the same as the weight force. Okay, that'd be one thing. A rocket, either a water rocket or a fireworks rocket, has a change in acceleration. The force doesn't change there, Stas. What changes that time? Yeah, because the mass as the fuel is burnt off, the mass changes as the mass gets less, then the acceleration actually increases. And seeing as it's such a sunny day, I think what we'll do is take the water rocket outside and just try that for old time's sake. It's ejected. What actually makes the thing go upwards?
Pushing the water backwards.
Okay, so the bottle pushes the water, and the water provides a reaction force which actually drives the thing up. So that much you should know from...
Wait for you.
Anything else which changes its acceleration? A rowing boat. Why does a rowing boat change its acceleration? Okay, so as you're pulling on the oars, if you're changing the force, you're going to get a change in the acceleration applied due to that. Okay, you've also got a change in frictional resistance as well. Okay, so that would be another example. Anything else? It's going to have a changing acceleration. No? Yes, the simple harmonic motion that you've been starting off with, Mrs. Monroe. That's an example where because the force is proportional to the displacement, as the force changes, the acceleration changes. And in fact, the acceleration in simple harmonic motion is constantly changing. So we'll come back to that. So we'll look at the rocket later on this morning. You've looked at the idea of terminal velocity, where things are falling through the air and the forces change. Let's just say that you've got an acceleration where the acceleration depends on the time and it's proportional to the time. So say that you've got acceleration is proportional to the time that you're going for, so that the longer something's moving for, the higher the acceleration is. And that would be the case of Stas' rocket there. So if we plotted an acceleration time graph, you plot the acceleration would be increasing as the time goes on. So if you've got d2s by dt squared will be equal to a constant multiplied by the time. Now, it could be a number, it could be a constant factor. We'll just call it k for the sake of simplicity. So you've got k times t there. But as being that, the acceleration is proportional to the time. If we wanted to get the equations that define this motion for this much more complex motion than something simply falling with constant acceleration, what process could we go through that would give us the velocity and the displacement of this fireworks rocket or water rocket? It's very similar to something we did last week. You might want to have a quick look back through your notes. Don't worry, Andrea, you're off the hook for this one. All right, Tagai, any ideas? What could you do with that acceleration equation to get its velocity and to get it? If you integrated the acceleration, the acceleration is actually dv by dt is k times t. If we integrated that, we'll get velocity. So if we so WRT is just with respect to, so we're going to integrate with respect to time. So the integral of dv by dt with respect to time is going to be the integral of kt with respect to time. Integral of k times t with respect to t. The two rules for integration are, remember, raise the power, divide by the new power. So what would that end up as for the equation for velocity now? Nicola, what do you reckon? No? Well, raise the power, divide by the new power for integration. Alistair? Okay, so you get t was to the power 1, now t to the power 2, divide by the new power. And there's something else which you'd need to put into that integration. What else would be missing there, Andrew, that you'd... Yeah, you'd need a constant. So at that point, you would need to know, at time t equals 0, was the velocity equal to 0, or was it equal to an initial velocity? So you'd have kt squared over 2 plus your initial velocity. That would be the equation for final velocity. Yeah, Anna.
KT in brackets, is it just t to get squared?
It's just the t, so it's k times t squared, because it's only the variable that increases the power, not k as well. So k is just multiplying that. So it's kt squared without brackets, yeah. So that's our equation for velocity for this rocket or whatever. So you can see that if you were to plot a velocity time graph for a rocket, just try sketching that in your jotters. What would that look like, that graph of if you've got a rocket which sets off at initial velocity u, so it's been pushed up, thrown up in the air with initial velocity u, and then the rocket motor kicks in. What would that graph look like, do you think? Just try and sketch it there at the moment. So what do you reckon? Initial gradient is going to be... Yeah, it's pretty zero. So you've got a flat start to it, because that's a zero gradient. And then the gradient starts to increase. So what sort of shape are we looking at? Kirsten? Yeah. And mathematically, what would be the precise mathematical shape of that? Bear in mind that it's v is equal to kt squared over 2 plus a constant. Right? Yeah, okay, so we've got a parabolic curve here. And so velocity increases as the square of the time according to this equation. Okay, so we've got velocity. Now, to get the displacement, if you wanted an equation that told you that the vertical displacement that this rocket had taken as it goes up through the sky, what we're going to do to get the displacement? You must be clicking on to what's going on now. We've gone from acceleration to velocity by integrating to get from velocity. Yep, you'd integrate again. Okay, so we've got integrate again with respect to time. So we've got v is ds by dt. That's equal to kt squared over 2 plus u. So if we integrate ds dt with respect to time, you get the integral of kt squared over 2 plus u and all that with respect to time. The integral of ds by dt with respect to time is just going to be the displacement, s. And the integral of kt squared over 2. This is where it gets really, let's see if we can test you on your integration here. Same rule applies. Raise the power, divide by the new power. Who reckons they've got what that would be integrated with respect to t? Spot on, okay? Because we've divided by the new power. So we've raised the power 3 to 3, and we're going to have, what else? What would u be on that integral, Stas? Well, u is just a constant at the moment. If you integrate a constant, you are going to raise the power, but what's the power? If we've effectively got t to the power 0 here, so what would that become if you integrate a constant? No? Anna? Yeah, so it's u times t. So a constant in an integration, you are effectively saying that that's equal to u times t to the power 0, because that's equal to 1. So raise that power, it becomes t to the power 1, which is just t. There's still something else we've got to put on that integral. What's the last thing we're needing there? Donald? Yeah, we're needing a new constant, which would be the initial displacement. So S at 0 is the initial displacement, whatever starting height. Say if you set the rocket off at a height of 2 meters above sea level, that would be your initial displacement, S0. So you can make up these well, not make them up, but you can derive these equations if you know what the acceleration is by integration. If, alternatively, you were given an equation for what the displacement is for an object, could you get the velocity and the acceleration for that object? What process would you go through then? Anna? You would then differentiate it. If you had the displacement, you would differentiate it to get the velocity. And if you wanted the acceleration from that, again, you would differentiate it back to get the acceleration. So there's always this level of integration or differentiation going between acceleration, velocity, and displacement.